Hello everyone and welcome to today's cnWave webinar. Before we start, I would like to introduce today's presenters, Bruce Collins, the Senior Director of Product Line Management at Cambium Networks, and Anthony Holmes, the VP of Millimeter Wave Products at Cambium Networks. I also want to encourage everyone to ask any questions that you may have during the presentation in the questions tab on the control panel. But without further ado, I'll pass it off to you, Bruce.
Great. Thanks, Riley, and thanks everybody for joining today. We have a great crowd and a lot of really good latest breaking news and information about cnWave 60 gigahertz. Joined here with Anthony Holmes, and we're going to sort of tag team the presentation. We'll cover a number of topics, including really where we're at with a large number of customers deploying the products. We'll give you some examples of that. For those of you that are new to cnWave, we'll have a little bit of a brief introduction to that. And we're really going to do kind of a deep dive technical review of what makes cnWave unique in the 60 gigahertz ecosystem or market, and why we are today the leading deployment in the Teragraph ecosystem. More people are deploying cnWave 60 gigahertz than any other Teragraph solution. So lots to talk about. This webinar is being recorded and it'll be posted, and you'll be able to get access to it. We certainly will have plenty of time for questions, so really encourage you to drop those questions into the webinar interface, and Anthony and I will take those as they come, or we will certainly have plenty of time to cover that Q&A at the end. But without further ado, let me jump right into it. Anthony, I'm going to swing it right over to you and hand you the mic. You want to cover the first few things here?
Yeah, sure. I mean, as people know, Cambium Networks does a lot of different radios, and but with Teragraph, with cnWave 60 gigahertz, this is a different way of looking at how to deploy radios. We're really taking it down from the mast and into the street. You do not need to have any mast climbers to install this. It should be as simple as deploying a Wi-Fi AP with subscriber units using beamforming antennas. It's pretty much zero-touch installation, and it makes these solutions far more accessible to enterprise and non-telecommunication operators, as well as your general WISPs. So, what's changed? Cambium Networks started looking at 60 gigahertz back in 2010, right back then. And you know, this technology has been around, whether it's WiGig format or 11AD. But you know, we felt at the time it just really wasn't right for us to focus on. You know, the technology needed to evolve. So what's happened since? Since then, .11ay standard has come out. And as many people know, Facebook has worked with the standards to produce enhancements, which they call Teragraph. And we've been working with Qualcomm and Facebook for about over 3 years now, looking at this and how to bring a product to market. So what are the areas that's changed? So network capacity. Network capacity, we've got you know, large channels. These channels provide a lot of data, 3.6 gigabits per second in each channel. And channel bonding has the capability of increasing that, even doubling that rate depending on the platform. Scalability, lower deployment times. This beamforming allows you to have a lot of radios in the same area. Centralized management means you don't have to go and manage each one of these radios individually. You just do it as a whole from a single place. Dense deployments. This is one of the big difference. TDD, synchronized TDD frames. Those people that have deployed 5 gigahertz networks know just how important synchronizing your TDD frame is, allowing more units to work together. The single channel reuse, adaptive transmit power control, all these things allow that dense deployment rather than your typical pre-11ay or AD standard products. All this with network efficiency, with high availability, with cloud management, means there are many different ways you can actually use this technology. I call this, it's really this radio technology is the building block. It's a construction material. You can use this to do many different types of networks. Bruce, to you.
Sure. So, and to that end, you can see here 4 different topologies and how the product is deployed, and we see examples of this in all 4 of these around the world today. If you start over here in the upper left, you'll see a straightforward point-to-point solution, and certainly connecting point A to point B with a couple of gigabits per second is sort of a common deployment with this, whether you're connecting 2 buildings or a building to a camera or a building to an access point. You can see this point-to-point solution. In the upper right is a more traditional point-to-multipoint where I have a hub and a variety of spokes coming off of that. And we'll talk about how that compares and contrasts to the distributed mesh, which is down in the lower left, which is the ability to take one or multiple fiber pops, point of presence, or wireless pops, and bring them into a distributed mesh architecture, which allows you to distribute that that signal across large geographic areas. Even though each individual link is particularly maybe a kilometer or less, or even a few hundred meters or less in a mesh environment, you can cover large geographic areas by building out this mesh. So that's really the unique capability that 60 gigahertz AY brings, and the particularly with cnWave. You'll also see us kind of a special case down in the lower right is a small cell backhaul. And we call it small cell, but it really could be either a 4G or 5G small cell base station, or it could be a Wi-Fi access point. But effectively what you're doing is delivering gigabits per second to areas where you might not be able to reach with fiber, and you want to drop that in. So we do have customers deploying 4G backhaul today using cnWave as their transport layer for that for those deployments. So lots of different applications. Ultimately, what this means is people today are delivering gigabit per second to residential homes and businesses, and whether that equates to an actual gigabit per second package that you're offering as a service provider. We also have many customers and service provider operators deploying 250 megabit per second packages, 500 megabit per second packages, and really competing well against those cable operators as well as fiber operators. So this really is a way to compete or extend fiber for those of you that are in the service provider area. And if you're in the enterprise side and campus connectivity, I have some examples for you as well, but really it's a way to quickly move gigabits per second where I don't have access to fiber, or where I want to augment and increase the resiliency and availability of that connectivity. The portfolio itself is actually pretty straightforward. There's just 3 devices. You'll see here on the left is the distribution node, the V5000. This is the distribution node, or DN, is what makes up that distributed mesh architecture when you're doing that distributed mesh, or the hub in that hub and spoke architecture. The distribution node has 2 sectors. So that module that you see there covers 240-degree sectors. Each of those sectors can have up to 15 client nodes in that sector. And amongst those 15 nodes, 2 of those could be additional distribution nodes as well. So you can use that DN to not only serve client nodes, but also to serve subsequent DNs as I build out that mesh. And each one of those sectors today does the 1.9 gigabits per second upstream and 1.9 gigabits per second downstream in that sector. It's a shared capacity. On the client node, you've got really 2 options of the modules, but within the V3000, you can see there's 2 different antenna designs. Anthony will go into that in a little bit more detail on what's the sort of really innovative approach to how we've designed that antenna and some of the benefits that you'll see as an operator. And then we'll also talk a bit about the V1000 as a really small form factor, lightweight, and really useful in those residential access. So those client nodes can either be used as point-to-point links. So if I want to connect point A to point B with a point-to-point connection, I can use that, a V1000 to V1000 or a V3000 to V3000. And the difference in the two antennas here with the 3000 is really just a little bit gain versus form factor and size trade-off that you can decide to make in that case. And then any of these client nodes can also be a client node hanging off of a distribution node. A little bit more detail. We're not going to spend a lot of time going through specs and speeds and feeds and everything in this webinar. You can get all the data sheets from cambiumnetworks.com. But I do want to point out some of the flexibility and how they're deployed. So the V5000 and 3000 has 3 ports. You can run these with PoE with up to a 10 gig RJ45 connection. You've got an auxiliary port with 802.3 AT PoE out, which makes this a useful solution to power either a backhaul, or you can power a Wi-Fi access point or a video camera with the auxiliary port. And then it has an SFP plus port that supports a variety of different SFP modules for those that are bringing fiber directly into the V3000 or the V5000. One of the things that we're really excited about, we're seeing service providers really take advantage of, is the small form factor of the V1000. You can see there, it's literally the size of your hand, the size of, you can see in the photo there. And really what that allows you to do is deploy this in very unobtrusive areas. So you can hang it on a downspout, you can hang it on a pole, and it doesn't take up a lot of space, and it doesn't look like a big radio or dish. So you have this really small form factor that you can put there. Just as a comparison, we just selected one particular competitor that's out there in that Terragraph space, and that Cyclu product is 8 times the weight, 5 times the volume, and 3.5 times the power consumption. So you can really get a feel for how much integration and innovation that was put into the industrial design of the V1000. Is just very fit for purpose with the residential deployments. Anthony, you want to take us through a little bit about the unique design of that V3000?
Yeah, I just think I just wanted to highlight here that most people producing a dish in 60 gigahertz, they just use a single transceiver, a single just a patch pair. And the disadvantage of this is, I'm not going to go too much into the details, but Cambium Networks has got some really highly skilled antenna designers, and as far as beamforming is concerned, you look at something like the 450M, you understand, we're the world leaders in antenna design and beamforming. And what we've actually done here is, rather than just use that single pair, we've actually used the whole tile and be able to focus that energy into producing a compact, high gain antenna. The V3000 is the equivalent of a 2-foot dish in a lot smaller package. And the advantage of using all the patches for this is twofold. One, the actual conductive power is a lot lower than you normally would need. And basically that means you don't get as much noise, you don't get as much errors produced on the signal you're trying to produce, distortion. So it's got a huge advantage there. The other thing is you've still got beamforming on this, and we're going to go into a little bit more detail later that you can actually beamform with this. It will actually do periodic beamforming as well to keep optimizing the link, even in this P2P form. And you've got a plus and minus 2 degrees in that. Bruce?
So there's a lot of words on this slide, but I thought it would be useful just before we start digging into all of the technical differentiation of the product is to kind of have it summarized on a single page here. And so what you've got down the left is some of the key attributes, and we'll dig into these in some detail here in the session today. What sort of the status of this Cambium Network cnWave 60 is, and then how we see that as advantageous over some of the competition. So we'll start with hardware cost, and you can certainly contact your partner, your Cambium Networks partner, and get a quotation on what these products cost. Because of the clever use of the V3000 and its long range and high gain antennas, combined with that two-sector design, we see that in most applications, the cost of deployment of a cnWave is about 30 to 40% lower cost than the competition. And so it comes from a couple of things. It comes from the lower cost CNs. It also comes from the ability to deploy a two-sector single channel deployment with the V5000 DN. Terragraph compliance. Cambium is committed to the Terragraph ecosystem and working with the Terragraph interoperability requirements. And so therefore we're going for full compliance with Terragraph, whereas some of the competition out there, you have to be careful whether they're supporting the full compliant Terragraph with complete mesh support, with complete management support, and kind of make sure that you're looking at solutions that are fully Terragraph compliant. The flexible and scalable networking. This really is a modern, latest generation product. It has internally under the scenes, or behind the scenes, or under the cover is layer 3 BGP routing. It has this open arm mesh technology, which really is light years ahead of where mesh protocols were 5-10 years ago. Supports IPv6, again, under the hood and behind the scenes. But of course, what we've also done is introduced features that make the whole system look like layer 2 and IPv4, so it easily integrates into your existing service provider network. So what we like to say is you can do layer 2 or layer 3 with this product, it's your choice. You can do IPv4 or IPv6 with this product, it's your choice. So really, you've got a lot of flexibility. We'll say many customers are deploying this with layer 2 IPv4, and it is a nice, easy integration into your existing network. Link budget, we talked about. Anthony covered that quite well with the V3000. The mechanical design, we covered that as well. You've got the small form factor CNs, and watch this space for some more designs coming down the road. But our goal is Cambium, with our long history of deploying millions of radios. Our focus is always low power, low weight, low volume, fit for purpose CNs and subscriber modules and throughout our portfolio. So you'll see that continue. The distributed mesh architecture is new, and we really are leading the way on deploying this in the 60 gigahertz 11AY Terragraph approach. It's available, it's out there, it's working. Customers are deploying hundreds and thousands of customers on this distributed mesh architecture, and it's been proven to work. So really encourage you to take a look at that. Management, there's a couple of different options there. You've got onboard management, as well as what we call our end-to-end controller. We'll get into that in a little bit more detail. But the nice thing is it's the same management interface, whether you're talking about a simple point-to-point link, a point-to-multi-link, or this full distributed architecture. And of course, this all fits nicely within Cambium's portfolio of other fixed wireless broadband and enterprise wireless solutions. So that's really a summary of what we're going to talk about. I do want to point out that there are we're not the only product in this space, and there are some what I call sort of myths that are out there about cnWave. So I want to kind of cover a couple of those. One of those is that, and we're going to kind of show you some examples here, is that cnWave really is a lower cost way to deploy 60 gigahertz. And again, I mentioned how that's done, but we'll go through that in some more detail. cnWave is Terragraph compliant. We have an E2E controller that can either exist on the POP node or it can be sitting in a virtual machine on the network. That makes it Terragraph compliant. That makes it easy to extend and manage, and resilient and reliable, all those things that Anthony mentioned about the great things about 11AY and the Terragraph ecosystem. Want to make sure and clarify that cnWave leaves the choice to you. You can do layer 2 or layer 3. You can do IPv4 or IPv6. We have long range V3000. We talked about that in some detail. So don't don't be steered wrong with the other information that might be out there. The V3000 has a 60.5 dBm EIRP, can do long range connections, and with the beam steering is really an innovative approach at both maintaining alignment, and also providing that high EIRP and that innovative package. And the meshing, one of the things that some people who have looked at mesh with pure Wi-Fi approaches, say 5-10 years ago, have been concerned about what happens in a mesh environment. And one of the things we'll talk about here in a little bit, but in reality, mesh is, this mesh approach is less than a millisecond latency and less than 250 milliseconds to recover or reconverge that that mesh if something happens or something happens in the mesh itself. So just wanted to kind of summarize that with the differentiators, and I'm going to go through and kind of cover a few different areas and specific topics around these and do a little bit of a deeper dive, and Anthony will help us walk through some of those as well. The first thing I want to do though is show you a real world example of a distributed mesh versus hub and spoke. This is a real world example here. This is a customer service provider wants to provide 500 megabits per second and gigabit per second capacity to this this area of homes. There's 55 homes in this neighborhood. When you're talking about 60 gigahertz, you have to think about really three sort of constraints when you're doing the design. One is 60 gigahertz, by the nature of physics, is a line of sight technology. So you must have absolute line of sight between the distribution node and the client node. To achieve that highest modulation, we use a rule of thumb of around 200 meters range. You can actually go a little bit longer than that, but in this design, the goal was to keep it to 200 meters or less. And each sector is 15 client nodes per sector. And again, that's part of the AY standard, that 15 CNs per sector. So you want to keep an eye on where you have the POP, where you have the distribution node, where your sectors are. You can do no more than 15 CNs within that sector. So you kind of have to think through where you're going to have that POP or where that fiber is present. So there's really two approaches to this. There's the traditional hub and spoke approach, which you might be familiar with if you're deploying 5 gigahertz fixed wireless broadband. And then what we'll show you today is an alternative to do distributed mesh. And it's important to know that we can do both with cnWave. You can use this as a hub and spoke and it works just fine. You can also do distributed mesh, which we believe is the more future-proof way of deploying this and more economical and economically scalable way to do this is with that distributed mesh. And I'll kind of show you the A versus B here. If I was going to do traditional hub and spoke, you might imagine having a single point of presence. I have a tower here that I have a fiber node at, and I'm going to build a tower there that then can look out over the horizon and see all of these different homes. Well, as it turns out, if I'm going to hit all of these homes with pure line of sight, I want to get up to 96% of the homes, I need to have a 30-meter tower. So that's a 100-foot tower, and this neighborhood's not going to be too happy about a 10-story tower coming into their nice neighborhood here. And if I go with a 10-meter pole, I can only hit about half of the homes. Also keep in mind that because of where this tower is located, I may already have exceeded the 15 client nodes in this sector in this sort of southwest quadrant. And I've got some CNs that are sort of out here on the edge. They might start to drop in modulation because they're further away from that tower. And of course, a single tree can block that and prevent hitting certain homes in an area just based on line of sight. And I have all my eggs in one basket with that hub and spoke. Now, not to knock that this is still a legitimate or viable way of deploying it. It's just there are a number of constraints in how you deploy 60 gigahertz in this approach. What we recommend or kind of see as a great alternative is what this distributed mesh capability provides. And what you see here is a design example showing 7 distribution nodes spread through that neighborhood. The benefit is that none of these are more than 10 meters tall, and some of them are actually quite a bit lower than that, right, connected directly to the rooftop of the home. The benefits you get are you can see that it's reliable. Most homes are covered or can have line of sight to multiple distribution nodes. So you've got resiliency. If one DN goes down, that client node can see more than one. All my links are shorter, which means all my links are higher modulation and more capacity. I have fewer CNs per DN. And really on the scalability side, it gives me a lot of additional, I can start to add additional homes off of each of these DNs. And even more importantly, if I want to extend this network, let's say I wanted to go off in the southeast direction here, or if I want to extend off to the north, I can just add an additional distribution node, and that will extend the mesh, interwork with the rest of the mesh, and I can sort of extend where the customers are and where the demand is coming from, rather than building out some long-term capital plan of where I'm going to place my towers. I can extend in a piecemeal fashion to hit all of those new customers as they come online. So that's kind of the contrast. Here's another example just to kind of show you a sort of an ideal case for a micropop application. And a hub and spoke. So it's just sort of this is a little bit of a contrived example because it really sets the absolute best case scenario for a micropop design. I have a micropop. It's located central location with all of the homes evenly distributed around. I have a second location again with homes evenly distributed around. But even in that idealized case, we'll show you this example, is that even in this case, a distributed mesh can often provide better functionality, resilience, and scalability. You can see that in the lower left, by using 6 distribution nodes, I can again reach all of those different areas of smaller number of CNs per sector. All the links are shorter. It's easier to expand out at the edge. If I want to go and eat off in any direction, I can continue to add additional DNs or CNs off into each individual direction without adding additional complexity of towers and power and all that other stuff. And ultimately, some examples here, these are just sort of based on some sample pricing and list pricing in the market, and comparing the cnWave solution using a distributed mesh and the alternatives of some other products that are out there that use a 4-sector design and are more tailored to that hub and spoke architecture. The cnWave solution is 60 to 70% of the cost of that other alternative. So even by putting out more distribution nodes, you're actually able to save money by having higher capacity, cover more the client nodes, and again, more resilience and reliability as that network scales. I had one other example in here I'll show you, and then we'll jump back over to the technology side. This is a view of again, an area that an operator looked at to say, well, could I do 60 gigahertz wireless on the left, or could I do fiber to the home on the right? And you can see on the left a design using DNs and client nodes to provide coverage to all of the homes in that area. And on the right, fiber to the home requires a significant outlay of capital up front. I need to plan all of those trenches, cabinets, lay the underground cable, provide all of those splice points. And so the complexity of fiber, not only the cost per node is just 41% of the cost of fiber when I deploy this using cnWave, but the time to market is significantly faster as well. I can get this wireless network up and running, start collecting revenue from those subscribers significantly faster than waiting for all of this fiber infrastructure to be deployed. And then, of course, you also have all of the permits needed to trench and find ways to get that fiber to all these different homes. So visually, sometimes a top-down view looks simple, and then when you get out to the actual area, and now I'm going to actually go and deploy this fiber, things get more challenging. And here's one last example from one of our customers that this might also be kind of close to home for some of you that are here in North America. This is a small housing development with fiber on the edge of the network, and then you can see there's some existing copper, but it doesn't provide the gigabit per second capacity that they were looking for. So they had estimated that this project was going to be about $150,000 to deliver fiber to these homes, and then by using cnWave, it's about 1/10 the cost of that, using wireless and 60 gigahertz to deploy that cnWave, including putting in a couple of poles with solar power to extend that network across this region. So again, another example of why this is technology is really cost effective relative to fiber or other wireless alternatives. So with that, I'm going to hand it back to you, Anthony, and maybe you can take us through some of those other key differentiators that we talked about. This will be a little bit more deep dive, but I think it'll be helpful to understand the value proposition that we bring with cnWave.
Okay, so this is our PTP link that we have here at the Design Centre in the UK. It's around about a 1.2 kilometre PTP link. It's in the UK, so we're in region K. About 44 millimeters per hour is the 99.99% rainfall. So there's quite a significant amount of rainfall that happens here. Now, what you see here is this link running at 1.2 kilometers, and we are getting a bidirectional rate of 5.2 gigabits per second. This, I would say, would be one of the fastest 60 gigahertz links that you will see. That's for sure. Now, what this is channel bonding. So coming up later this year, we'll be releasing channel bonding for all the products. And what this gives you is either the more throughput. As you see, we're looking to edge, certainly on the PTP 3000, we're looking to get over 6 gigabits per second. But also instead, it'll also give you more range as well. So because we're channel bonding at a low modulation mode, you should be able to get a greater range. This is the equivalent of, anything without rain. That's the equivalent of you can get around about, you can still get a gigabit around about 5 kilometers. You'll be able to get a gigabit per second. Now in that rain region, we very rarely see this link drop. When I say very rarely, it has dropped once, and that's when we had something like 200 millimeters of rain in an hour. Obviously we didn't have that much in an hour, but we did have a sustained period over a few minutes, which was an enormous amount of rain. Now we've got something coming up to actually help out when you get that freak rainstorm. But I just wanted to leave this in your mind that this technology is not only about distributed networks, but also high throughput point-to-point links as well. Go to the next one. So how do you align these things? So what you'll find coming up in the next few weeks is an alignment screen on the web page, which helps you guide you in how to align this radio to get the maximum performance. Now, as I said, this is quite unique in the fact that it will do beamforming plus or minus 2 degrees in the azimuth. But it will also, you have to get it pointing in the right direction. So we have a number of optical aids in order to do this. We have a scope mount, but we also have just a little sight on top of the unit to get you pointing in the right direction. Once you're there, we now have this mode where you can log in and it will actually guide you using the RSSI. We have a history on there, so you know if you know what your peak was, so you can actually go past the point and really home in on the best RSSI for that link. This technology is you're talking about something with a 60 dB MEIRP or a 40 dBi antenna. You are talking the beam width here is 0.8 degrees. So in order to not only have optical alignment, RSSI alignment, but also the beam steering as well, ensures that you get a link with the best performance possible. Okay, so Bruce mentioned a little bit about teragraph compliancy. Why are we so interested in teragraph compliancy? So just to let you know, actually teragraph compliancy is at 3 different levels. It's not just about the Mac and Phi, which is the chipset level. That's great, that actually gives you your TDD synchronization. It gives you your automatic transmit power control and things like that. So that's good. But it also comes at different levels as well, where node levels, where in theory you can actually swap out nodes for different vendors if you wanted to go that way. or even at the network level, where you can actually use multiple network managers to manage your network as a whole. Now, clearly, people have, even if you conform to the standards, you can have additions and things which make your products better. And you'll see that as we go through some of the things we've got with our layer 2 functionality, layer 3 functionality, and our network management as well. But Telegraph compliance here, there's multiple levels. The end-to-end controller, this end-to-end controller is an important feature. This centralized controller, whether it's running on a POP node or whether it's running externally, is actually really essential for running of your network. And you can decide where you want to run it to actually grow your network. The end-to-end controller as well for resilience, whether or not you want to run it in a unit outdoors or whether or not you want to run it in your NOC, you have the choice. Now, what the end-to-end controller gives you is the ability to have these features: interference mitigation scanning, network topology discovery, where you can actually discover your network underneath you, and you're able to see what's going on in your network. Coordinated beamforming. Now, this coordinated beamforming means that each radio is scheduled to actually keep on doing periodic beam scans and able to optimize the performance of each of the nodes. By coordinating that, you won't get interference. Golay codes. The .AD standard only had one of those. We can use 4, and we're looking to expand that to use different, even more Golay codes. Now, what are they? They are the ability to sort of color, a bit like color codes, color your signal in order that you know where it's coming from, and therefore you can ignore signals which might weak interferers, which might get to you and you're not really interested in. So Golay code optimization will have a look around the network and optimize the codes to reduce interference with units located close to you. Super frame optimization. The frames are actually, you have multiple frames and they're divided up. Again, this is about optimizing that. Working in that large network, you're able to distribute the processing power and the throughput of the network. So multiple POPs as well as another one. Every POP you add, and we're going to show you some examples where we have large networks with 5 or more POPs. Every POP you add, you get another 3.6 gigabits per second capacity in that network. So as your network grows, and you suddenly realize, you know what, I need to have more capacity. I'm sharing this out with so many CNs. You just pop in another POP, and you can connect that via fiber or connect that via license-based microwave. And again, that whole network gets that capacity. And I'll talk a little bit about that in layer 3, how automatically the network will optimize itself when it sees another POP. So we just want to emphasize that this is really what .11ay is bringing you, and we've taken this on board, and we're trying to utilize all these features in order to give you a complete solution. So layer 2 versus layer 3. So basically, I don't know what your networks are like, but I imagine most people have been using layer 2 networks in wireless for some time. Layer 3 networks and routing is more being for Ethernet traffic indoors and large data centers. However, it's actually clear just that there are huge advantages about going into layer 3 to be able to distribute your network. As your network grows with layer 2, you've got a lot of broadcast traffic flowing around, could overwhelm the network. The chances of having loops in your network increases as well, and especially if you're trying to do a mesh network. By using routing, you're able to eliminate that, and it enables you to actually get traffic out as quickly as possible. Now, in conjunction with, we're using BGP in this. So you can actually zone, it will automatically zone your network for you. So these zones, especially with the multi-pop, these zones give you the capability of dividing up your network based on the path lengths and the performance of those paths. You're able to divide those up to give you your optimal pop to exit your traffic from. So all this is sort of is hidden away inside the cnWave network. As far as just quickly go back a second. Just what I was going to say about OpenR. OpenR is the mesh technology. Now, Facebook actually originally developed this with Terragraph in mind. However, they realized just how useful this OpenR mesh technology was, and they actually use it in their data centers, connecting all their Ethernet switches and routers, well, the routers, I should say. And what this is, it's actually monitoring the whole network constantly, taking a look at keeping a database of all the paths to actually exit exit the network. So what happens if there's a break anywhere, the convergence time for meshing is pretty instantaneous. It already knows what the best route is to go to next. So we're talking about, we can detect a breakage in around about 25 milliseconds, and we can actually switch in under 250 milliseconds. So it's pretty rapid as far as that's concerned. Now, all this, most of you guys, or most of your networks will be using layer 2. So to make this invisible to you, we actually put layer 2 on top of this, and the next slide we can go into. So layer 2 bridging is one click away. When you get your unit out of the box, all you have to do from the centralized management system is go, I want to do layer 2 bridging, click enable. As soon as you enable that, you basically are able to facilitate the bridging of IPv6 across your network. The nodes will form tunnels to the best pop, not just any pop. It will actually, using the layer 3 underneath, using the routing underneath, it is actually able to form to the best pop. Now, if that pop goes down, if a link goes down, all the meshing still works. The tunnel just diverts itself around the problem or diverts to the next available pop. So again, this is all invisible to you. If you just want to run this as an IPv6 network, if you just want to run this as an IPv4 network, all the layer 3 and the routing and the IPv6 connectivity inside that island of cnWave is just invisible to you. Actually, I'll just mention, as far as IPv4 is concerned, we also have the sort of rich layer 2 functionality in there, VLAN tagging, whether it's single tag, double tag, remarking, priority marking, DHCP v4, option 82 as well, will be available in a couple of weeks. Now, spoke a lot about mesh, so again, this is the most simplest mesh network you can have is just a ring, but this is very simplistic. We've got some examples here where we've got 100 nodes doing mesh. So as I said, each of these individual nodes knows where that best route out is, and as I say, we work in zones, we work with multi-pop, and the actual meshing can cut over and converge in less than 250 milliseconds. Simple management. If any of you have used Cambium network equipment in the past, CM Maestro is basically the manager that we would say controls all of our technology, whether it's 5 gig, 3 gig, LTE. And now cnWave, you can all manage it from that single place. And so cnWave is integrated into that. We have many ways of doing this. As I mentioned, you can have the onboard end-to-end controller, ideal for point-to-point links, so it'll control those. In the meantime, that single one can also do the micropop approach, the hub and spoke. Again, onboard controller, or you can have it externally at that stage. One Maestro can control many end-to-end controllers. So that's the example of the external one. And then, of course, you can then expand that and have that as a full mesh network. Network planning tools, and we have a number of network planning tools. Link Planner now supports mesh planning. So you can put in your CN, your V5000, your 3000 and 1000, and it will be able to predict quite accurately. It actually uses all the antenna patterns, all the gains, all the powers from the actual units themselves, and it can predict the throughput and the availability you get. With Link Planner, it deals with rain regions as well. So down to 30 meters, it's using the data from the ITU in order to tell you what kind of rain region you're in, what kind of millimeters per hour you might expect, and therefore the availability. If you use that, you'll be able to design a system which is robust and resilient. CN Heat, it has the ability using LiDAR data to look at coverage plans. And then for large deployments, we have working with channel partners, we have a tool called the Advanced Network Planning tool, which enables you to do large plans, to look at the total cost of ownership, the CapEx calculations, and it is able to give you the optimal position to put your DNs in order to do that distributed network. Now, along with the installation tool, I don't know if people have used it before, but we have a tool called CN Archer, which is the mobile installer application. So basically, this, if you see, these are some screenshots from it of the V3000 install. What you're able to do is some very quick and simple things. When you're deploying cnWave, it is pretty much zero touch. The only thing you actually have to enter in there is if you're using wireless security, you will have to put in your certificates for 8021X. So you're going to have to put your keys in for that. However, apart from that, all the configuration is downloaded from the end-to-end controller. So you don't have to put anything else in other than just a quick start. So this mobile installer allows you to do that, but it also, as you can see, enables you, if you haven't got your laptop there, enables you to see that alignment window, and you are able to use this to align your V3000 with that.
All right, thanks, Anthony. I think let's spend a few minutes. I'll give you some examples of how customers are deploying cnWave around the world today. So people are deploying gigabit per second, 500 megabits per second, 250 megabits per second service packages to residential and business customers. They're also connecting campus connectivity, building to building, building to access points with gigabits per second as well. So lots of examples around the world. Tens of thousands of these radios have been shipped all over the world, and deployments are happening every day. We hear more and more of these antennas going up on the air, and you can see pictures of those. And there's always more pictures and examples coming up on our community forum as well. Here's an example of a network that was done at the city of Aurora, Colorado early this year. So this project was really to take an existing infrastructure for the city government. They were using some aging 50 megabit per second point-to-point links, and they upgraded the entire network to deliver 500 megabit per second and gigabit per second point-to-point links, covering all of their infrastructure, remote buildings, and provide some coverage and access for the city workers as they go around the city and provide services to the citizens. Anthony, you've been intimately involved in this one. You want to comment, make a few comments on the smart city application?
Okay, this smart city application is a really neat one from the requirements from the city, which was to provide a digital infrastructure throughout the city to put Wi-Fi APs to offer Wi-Fi access to people, and also to in key customer areas, residential and enterprise, offer gigabit radio services. So that's the top left picture is the sort of requirement. Now, what we did is we took the bottom left picture is what AMP produced as where we should be putting our distribution nodes and where we should be putting our POP nodes. And then the picture on the bottom right is actually the CN Maestro screen of the network up and running. This is going to be going live to customers at the end of the month. So there'll be announcements on that at the end of the month, but it's around about 100 nodes offering Wi-Fi access points on there. There are 5 POPs in this, all working to provide that gigabit access to each one of those nodes.
Okay, and then here's another example. This is a service provider in Perth, Australia, on the western side of Australia. And what they're doing is using the cnWave to deploy high capacity and low latency services to homes throughout the area. So they're leveraging some fiber that they have around the area, and they're extending that to these homes. You can see some of the images of the deployments. They're also using some wireless for backhaul. So they have fiber points to some certain POPs, and they're using our wireless licensed microwave links to provide additional extensions of that mesh, all ultimately deploying a large number of client nodes and subscribers, again offering anywhere from 250 megabits per second up to a gigabit per second service plans. Here's another example, and this is sort of indicative of what can be done for campus connectivity. So you can imagine those rings topologies that form the mesh that Anthony was referring to. And then also, how do you extend across, for example, this highway, or it could be a river or another area where I can't trench fiber, but I can extend that with a client node to the other parts of the facility or the organization. So again, lots of ways to extend gigabits per second across a wide range. And this is a private campus area network. On the industrial side, here's an example of a deployment in a rail yard where they placed distribution nodes down each side of the track or the rail yard, and they're using this to provide video surveillance, process automation, telemetry, and provide lots of capacity across this entire rail yard. And you can see that the rings and mesh being formed by providing these links across the yard. And then we mentioned that there's some examples in the small cell backhaul arena. This gives you an idea of how it's possible to use 60 gigahertz to extend and place those small cells down, in this case, a narrow street where trenching fiber would be difficult and aerial fiber may not be reliable. And also I don't have line of sight, but I can extend this with some relay nodes and provide that series of small cells within this existing urban area. I'm not going to go through in too much detail on the roadmap, but I wanted to highlight that if you're currently using cnWave 60 gigahertz, the latest release is 1.1. There will be a 1.2 beta release with some of the features we showed here today. That will come online and be available to you around the end of this month. And then we look to have that fully released and commercialized in early September. And then the development on cnWave continues at a rapid pace. And some of the features we talked about, like channel bonding and some of the advanced analytics, are coming down the road, and you'll see those coming soon. But suffice it to say, this is a very active development for Cambium. We are all in on this, and we believe that, and we know that we're the leading deployment in as far as number of radios that are out there today using the AY and Teragraph standard, and we look to extend that. And it's feedback from customers like yourselves that help us drive this roadmap and steer it in the right direction. So always interested in your feedback as well as far as what you'd love to see coming next. One feature that we did mention briefly was the ability that Anthony mentioned was the ability to add a 5 gigahertz failover link. So I can deploy this in a shotgun fashion where I have my 60 gigahertz point-to-point link, and then in parallel, I can put a 5 gigahertz link, whether it's our PTP 450 or an EPMP point-to-point link, and basically provide that extra resilience, which allows me to both extend the availability but also extend the range, because I can push to a farther range and have that fall back to 5 gigahertz in case of a fade situation. And with that, I know we're running a little bit long. I wanted to save a few minutes for questions. I'll pop this up here just to kind of show you where 60 gigahertz fits into the overall Cambium portfolio. And you can see that this portfolio continues to expand. And whether you're looking at hundreds of meters out to a kilometer or so with gigabits per second, you can do that with the cnWave. You've got outdoor Wi-Fi, indoor Wi-Fi. Of course, you have our fixed wireless solutions with PMP 450 and the EPMP platforms. Soon to come, our 28 gigahertz solution. And then that all ties together with the management platforms we talked about, including our enterprise grade indoor or enterprise grade CN matrix switches, and especially point you to the TX switch, which is especially well suited for the service provider because it provides things like power and sync for our fixed wireless solutions. So I'm going to pause there. There's a few questions that came in. I certainly encourage you to ask additional questions if you have any as we come to the end here. First question here, and Anthony, you and I can kind of maybe both tag team these as well. How many DNs can be deployed on a single tower? There's a couple ways to think about that. I don't know if you have initial thoughts on that, Anthony.
Well, okay. As you know, this product has a wide coverage of 280 degrees. That said, you can actually overlap these. The adjacent channel interference is such that that you can actually have them on adjacent channels. If you are going to put them on the same tower, I certainly would advise that. So 4 of them on a tower will be possible.
And then the range on a V3000, what are we recommending for in a point to multi-point environment? I believe the question is.
Well, I actually even doesn't really matter about whether it's point to point or point to multi-point. The range is the same. But obviously a V3000 to 3000, as I say, I think the longest link that I know of is around about 1.4 kilometers out in Malaysia. But people, you can go longer than that. As far as it's concerned about a 5000 to in a multi-point situation. Sorry, get my words out. So that's a V3000 to a V5000. It really does depend on the rate. If you want to get about a gigabit per second, so if you want to get MCS 12, you're talking about 600 meters. 1 gigabit, you should be able to have well over a kilometer. That's with no rain. As soon as you go in a rain region, it will drop. So if you're talking about 4 nines rain, yes, you are talking around about 200 meters. But that's still one of the longest ranges that you'll get on a 60 gig radio. And that's only with a single channel bond as well. If you channel bond it, you'll get a longer range. I really would advise you use a link planner, and that would actually tell you what kind of ranges you will get. It is pretty accurate.
There's another question here about putting equipment and power supplies at a home that is a mesh node site. So I think we see service providers doing this in different ways. So effectively, when you look at those distributed mesh architectures, one approach is to put the distribution node on one of the homes that you're serving. So we call that a donor home. And in that case, you can either put a power supply on the accessible power supply on the outside of the house. You can also do a traditional PoE injector inside the house. And then it's kind of up to the service provider how much sort of battery backup they'd like to apply to that in that particular approach. Now, we also see service providers putting these on sort of a small mast or a rooftop in a commercial area. So there's lots of other deployment methods and in how people are deploying these. It could even be a wooden pole that is planted in the ground and apply it there with some solar power. So there's a wide variety of different ways of doing that. Looks like there were some questions about supporting mesh in Link Planner. So so William, you asked that question. I see Anthony gave you some links to click to. I'd always encourage you a question like this to go to our community.cambiumnetworks.com, and you can ask these kind of questions, and either somebody else that's run into the same issue will comment, or certainly one of our support or development or product line management team will get back to you quickly on that. So suffice it to say that you can do mesh planning in Link Planner, but we'll help you out and get you going on that. And then let me just read this last question here. Anthony, are you able to see that question? I'll read it out here and then maybe comment on it. Where there's multiple POPs that have different public IPs, how does routing perform with end user devices via the mesh network?
So, okay, there's many ways to answer this. If you're talking about layer 2 bridging, they've got to be on the same subnet. If they're on the same subnet, then they will be able to communicate with each other. We also make sure that the OpenR interface, if they're on the same subnet and you want the POPs to talk to each other, you make sure OpenR is working on that interface. If you're on IPv6, then you've got to have routable addressing, and again, that will find that. But then if I look at this end user devices via the network, that will be down to your equipment. You would have it will go to your routers, and then that one would decide how that would then get back into the mesh if it needed to. I'm not sure I answered that, but if you want to reach out to me with the actual example, I can go into that deeper.
All right, well, thanks, Anthony, and thanks again for everybody joining. I know we went a little bit long today, but there was a lot of material to cover. Appreciate the questions that you had. If you have more questions, you can certainly post them on the community and we'll follow up. And I think I'll wrap it up there. Riley, back over to you if you want to have any closing comments, but again, really appreciate everybody joining today, and we'll talk to you down the road.
Yeah, thank you so much, everyone, for joining us today. And thank you so much, Bruce and Anthony, for all the helpful information. We will be sending out a recording of the webinar to all attendees shortly, and we'll also be posting it on our website as well as the community, as Bruce said. So be on the lookout for that. But until then, enjoy the rest of your day.